Get started. Welcome to the University of Tennessee Nuclear Engineering Department Colloquium Program. My name is Lee Dodds, and it's my privilege to introduce today's speaker. But before I introduce today's speaker, there's someone else I want to recognize. One of our professors recently was elected as a fellow of the American Society for Mechanical Engineers, ASME, and it's Dr. Art Rogels. And so let's give him a round of applause. Let's stand up. Wave. And okay, now for today's speaker, who is our own Dr. Bob Uhrig, who is a distinguished professor with joint appointment with the University of Tennessee and the Uhrig National Laboratory. Bob received a B.S. in Mechanical Engineering from the University of Illinois in 1948 at the age of 19. And then he received an M.S. in Engineering Mechanics from Iowa State in 1950, which was followed by a Ph.D. in Engineering Mechanics from Iowa State in 1954. And then he went into the service, and in fact he was assigned at West Point. He was an officer, and he taught at West Point from 1954 to 1956. And then he returned to his alma mater, Iowa State, and he was on the faculty there from 1956 to 1960. And then he got the call to go help start up the nuclear engineering department at the University of Florida, which is what he did in 1960. He became a professor there, and within a year or two, he was head of the department at the University of Florida. It's on, guys. We got a problem? Okay. He was actually head of the department until 1968. And then in 1968, he became the Dean of Engineering at the University of Florida, a job he held until 1973. And in my long relationship with Bob, he said that's the toughest job he's ever had in his life, is being Dean of Engineering. Then he joined Florida Power and Light, a nuclear utility in Florida, in 1973. He was their vice president for research and development and advanced systems. He was there until 1986, when he came back to the University of Tennessee and the Uhrig National Laboratory in his current position as a distinguished professor. He's now in the emeritus status, but being emeritus, all it means is that his money comes from a different source. He still works very hard and participates greatly in our program, for which we are deeply appreciative. He went into that emeritus status in 1998. And my last comment here, I'm never going to let him retire. That's a nuclear engineering decree. And so his topic today is nuclear energy for hybrid electric vehicles. Ladies and gentlemen, please welcome Dr. Bob Uhrig.
Thank you, Lee. Every time I hear somebody read off the pedigree, I think of the situation that basically is that I'm becoming an old fogey and I couldn't hold a job very long at any one time. But anyhow, I'd like to talk to you today about the hybrid electric vehicles. It includes the automobiles, SUVs, panel trucks, pickups, all the so-called light vehicles that burn gasoline, the four-wheel type. And we're going to relate this at the end to nuclear energy, so there is a connection. The hybrid cars were conceived back about 100 years ago. This is 1903 Krieger hybrid electric automobile. It is reputed to be the first vehicle of this type built in the United States. In the way of background, the hybrid concept has proven to be technically valid and works quite well, but there really wasn't much interest in it until late 1960s. And, oops, got too many. Anyhow, the thing that happened in the 1960s was that we have a new set of environmental conditions imposed upon automobiles, the reductions in emissions that was rather drastic at the time, and this was viewed as one of the possibilities. So Congress finally got around to passing Public Law 94-413, Electric and Hybrid Vehicle Research, Development, and Demonstration Act of 1976. And they ordered the newly formed Department of Energy to pursue the technologies associated with electric and hybrid vehicles. So DOE dutifully undertook a number of studies, many tests, developed experimental components and systems, and built a number of cars. I'll show you a couple of those of that era here in a minute. What happened here was that at about the same time these vehicles were being developed, the energy crisis went away, and almost simultaneously the automobile industry was able to apply digital microprocessing units to improve the fuel mileage, almost doubling it. And there was also improvement in the exhaust after treatment of to reduce the amount of effluents going into the atmosphere. And as a result of that, industry really wasn't interested in the hybrid because they had already done their job, they had met the standards, and they really didn't want to mess around with something that was more expensive, heavier, and more complex. Now, what happened at this point was simply that there was very little interest, not much work continued, with a couple of exceptions. One of them was the Electric Power Research Institute was very interested in this as a possible new source, new market for electricity, where they would use the electricity to charge the batteries rather than depending entirely upon petroleum. So that's where we stood until three or 4 years ago. Let me talk a little bit about the kinds of configurations you might have here. First of all, there is the series hybrid, where you have the gasoline engine that drives the generator, charges the battery, which runs the electric motor and drives the wheels. And the parallel configuration down here, you can use both the gasoline engine and the electric motor to simultaneously give power to driving the wheels. And of course, there's always various combinations of these two choices here. I got interested in hybrid vehicles about 1973, when I was at the University of Florida. And one of the projects down here, Dr. Vernon Rowan of the Mechanical Engineering Department built a small hybrid using a Datsun chassis. And the drive in this was a 14 horsepower Onan motor generator set. They had 8 lead acid batteries. I think they were Sears diehards. And they used the series configuration that I just showed you there. It was capable of 80 miles an hour maximum speed, but you couldn't keep it there because the battery ran down. So, but it was able to maintain a speed of about 50 miles an hour, even though it's only a 14 horsepower source of energy here. And this is a picture of it. It was actually a chopped down Datsun chassis. I think they shortened the rear of it. Otherwise it looks pretty normal for a Datsun of that era. They also dealt with a hybrid city bus, 24 passenger, a 30-foot bus. They put a 60 horsepower John Deere tractor diesel in it, and driving 2 15 kilowatt generators, 2 custom lead batteries, 1,800 pounds apiece. And it was capable of 45 mile an hour continuous operation, but it could get up to 60 if you needed to. The range was about 300 miles, and they loaned this vehicle to the Environmental Protection Agency for testing mostly for mileage and for emissions testing, and it averaged about 8.5 miles per gallon of diesel fuel, which is probably approaching twice what that size of bus would get in normal service. This is a picture of the bus. It looks pretty normal from the outside. Now, let's talk about why hybrid vehicles are very responsive and still are very efficient. And the reason is that acceleration or responsiveness is produced by torque. Now, in a gasoline engine, the torque is relatively modest. It's low at the low RPM. It goes up, hits a peak at about 3,500 revolutions per minute. So you have to use gears to multiply the torque in order to get the acceleration that most people seem to want in an automobile. On the other hand, the electric motor has its maximum torque at 0 RPM. And it remains relatively flat out, usually beyond 1,000 RPM. And on top of that, the torque is several times that of the comparable gasoline engine of the same output. So when you use both of these together, what you've got here is a hot rod. It accelerates very rapidly and still has the power of the gasoline engine when it gets up to speed. And in fact, as we will see, they've set some new speed records. Now, the reason why they are so economical is that you have this gasoline engine here and you run it at its optimal point. This is a plot of specific gas consumption. The number of pounds fuel per horsepower hour output here, and it typically occurs somewhere between 75 and 85% of the maximum power. And that's what's happened here. This happens to be the curve for that John Deere diesel engine in the bus that you saw a few minutes ago. Now, the strategy in designing a hybrid is to use a small gasoline engine, low fuel consumption, operated at its optimal point, and you stop the engine when you come to a stop sign and sit there and wait without burning any gasoline. You also have regenerative braking here, which recovers part of the kinetic energy and converts it into electricity, which is then stored in the battery, and it's available for future driving of the vehicle. Now, let's talk about the types of hybrids that we have. These are the three that are available today. The micro-hybrid, or the so-called start-stop hybrid. When you come to the stop sign, it stops, and we have an integrated electric starter and generator alternator that starts the car up when you push in the foot feed, and simultaneously it starts the engine, and you resume operation with both the electric starter and until you get accelerated to where you want to, and then you run continuously on the gasoline engine. You're going to see a lot of these probably in the future because they're relatively inexpensive to implement this technology in existing vehicles. There is the mild hybrid, or the so-called integrated motor assist. The hybrid has a small electric motor that supplements the gasoline engine, but the electric motor itself cannot drive the vehicle by itself in any reasonable way. So it's really just given an assistance during the acceleration period. And then we have the full hybrid, the Toyota Synergy system, the Prius, that you're probably familiar with. The vehicle can run on gasoline, or it can run on electricity, or it can run on both, depending upon the circumstances, and it has a system for optimizing to produce the maximum fuel efficiency. Now, here is a schematic diagram. There are four of these here. The first two is, again, the micro-hybrid. Compare that to the standard vehicle. It has a smaller gasoline engine than the standard vehicle, which is not shown. It has an integrated starter alternator here and a reasonable sized battery, probably larger than the 12-volt system that most vehicles have. If you implement this, you can gain about 10% on the efficiency of the vehicle, If you have a vehicle that gets 20 miles to the gallon, you now get 22, 10% improvement. The mild hybrid, it has a smaller gasoline engine, a bigger battery, a separate alternator and electric motors, and you produce about 20 to 25% better mileage. So your 20 miles per gallon standard vehicle is replaced by one that produces 24 to 25 miles per gallon. The third one we talked about here is the full hybrid. And again, a smaller gasoline engine, a bigger battery, a bigger alternator, a bigger electric motor. And it gives you 40 to 45% better efficiency. So again, 20 miles per gallon is now 28 or 29 or 30 miles per gallon. Here we have the fourth configuration, which we're going to talk about today and see what its impact might be, the so-called plug-in hybrid. And it gets its name, of course, because you can plug into your standard electrical system at home and charge that battery. You don't need gasoline to charge the battery. You use the electricity. And you have a smaller motor, a bigger smaller gasoline engine, a bigger electric motor, a bigger alternator, and a bigger battery. Gas mileage doesn't really mean much in this context here, because if you're running with the battery alone, you can say, well, I'm getting infinite miles per gallon on my gasoline, which doesn't make much sense. But the idea is that you have a strategy to optimize the amount that you use from electricity and minimize the amount of gasoline that you would use. And we will see the consequences of this kind of a strategy here in a few minutes. Now, these are the hybrids that are available today. The Prius came out in the late 90s, and second generation came out in 2004, which is sort of the gold standard by which most hybrids are judged today. Ford has purchased the technology from the Toyota Corporation and are applying it to their Escape. I understand this vehicle is out. I don't think it made it by 2004. This chart that I have there came from Consumers Research. And this year, the Toyota Highlander is out. I know I've seen this. I have not seen this one, but I understand that it's going to be out very soon, the Lexus RX 400. These are the full hybrids. The mild or micro hybrids over here, there were a couple of GMs supposedly out in 04. And these two down here, the Civic and the Insight Hondas, came out in the late 90s. This is supposed to have been out this past year. I think it is out now. And here's what the future may hold. I won't spend a lot of time on that. Now, this is what the modern hybrid automobile, the Toyota Prius, looks like. It's a streamlined, relatively small car, but it certainly has all the fancy features of an attractive automobile. It has a nice display up here that shows you which components you're using at any particular time. It also gives you the number of miles per gallon that you're getting on this particular vehicle. Now, this is the system by which this operates. Let's start out with this corner up here. This is operating on the electric motor with energy coming from the battery into the Okay. Let's go back to that. Here's the battery back here. Here's the power control system. Here's the electric motor. And here is the front wheel drive. So the energy flows from the battery on through to the front wheel drive. Over here is power coming from the gasoline engine. It goes directly to the front wheels, but it also goes to the generator here, or the alternator, into the power box, into the motor, and on up to the front wheels. Over here, this has the additional feature that in addition to getting power directly from the motor, and also through the electrical system, you have power coming or energy coming from the battery, and so you have the full capability of driving the front wheels because the amount of energy that you can get out of the battery is not enough to drive this to full power. So you have to rely on some of the energy coming over this way to get there. Over here, this shows how you charge the battery. You come from the gasoline engine to the alternator, on back to the battery back here. But you also use the regenerative braking system where energy, the kinetic energy of the car when you're slowing down is transferred into this motor, which is reversed to become a generator, and into the power box and on into the battery back there. These are some of the characteristics. I think we can use this as an example of some of the interesting features of the hybrids. It's a 5-door, 5-passenger vehicle. It has a total of 110 horsepower available at any particular time. It's about 2,900 pounds, aluminum engine, 1,500 cc's. That's the type that used to use in the Toyota Corolla. So it produces 76 horsepower. It is a modern engine with double overhead cams and 4 valves per cylinder. But it has a measly torque of 52 foot-pounds, even at 4,200 RPM. So down around the speed at which you're accelerating, it's probably a third or a quarter of that value. On the other hand, the electric motor down here is a 67 horsepower motor, an AC synchronous motor, 295 foot-pounds of torque in the range from 0 to 1,200 RPM. And that's the speed that the range that you're accelerating in. So most of your acceleration in this vehicle comes out of the electric motor. And over here, the battery, of course, is a key component. You have a sealed nickel metal hydride battery. It only produces 28 horsepower. Notice that this is not enough to run this 76 horsepower, I'm sorry, the electric here, 67 horsepower. So you need some energy coming around from the gasoline engine to the electric motor in order to take advantage of that torque. Other things on here, I'm surprised that this is a 500 volt system and this is a 200 volt battery over here. Interesting feature, it has an 8-year warranty and 100,000 miles, depending on which comes first. It has a 12-gallon gas tank. And the figures from using the EPA standards, the city mileage is about 60 miles per gallon. The highway mileage is 51, which is a reversal of the typical arrangement that you have with most automobiles. And the overall is about 54. On the other hand, Consumers Research, who tested this vehicle independently, says it's not 54, it's 44. And when you get to range, EPA says it's 640 miles. Consumers Research says it's 520. But with the vehicle with only 12 gallons of gasoline in it, that's a long way to go for that amount of gasoline. It also has air conditioning available. I would guess that would be standard in most cases. That's one of the power-consuming devices that has always worried the electric vehicle people. It has an electronically controlled variable speed transmission so that you're operating the engine at its most efficient speed. And the dimensions are relatively modest. It's probably in the same category as a Honda Civic. But as I said, the weight is about 2,900 pounds. But this is a new world record for hybrids of 130.795 miles per hour. Now that's moving right along. I'm not sure I'd want to be in that vehicle that weight at that kind of a speed. But it's also true of the Honda Civic. The hybrid outperforms the standard vehicle by a considerable margin as far as acceleration and gas mileage, and almost everything else. Now, there are other companies interested. This is a Mercedes S-Class hybrid, and you'll note that this was a demonstration in Frankfurt in 1999. This is not a new concept here. The last few years, people have been interested in hybrids here. This has a V6 engine, and it has 2 electric motors. And the V6 engine gives you 245 horsepower, and the motors are relatively modest. The torque here is about the same as the Prius when you add the 2 of them together. So, and the motors are 41 and 34 horsepower each there. This is what Mercedes uses. Instead of a continuously variable transmission, they've got a 7-speed transmission. And the torque, if you look at this from those 2 electric motors, is together 583 foot-pounds. That would take that vehicle probably from 0 to 60 in less than 5 seconds, I suspect, which is the definition of a hot rod. Here is the configuration that's laid out here. This is not the same as the previous slide, but it's a similar one. Here are your 2 electric motors. Here is your V6 gasoline engine. Note what they've done here, and these are clutches that determine what drives what. The interesting thing they've done here is they've replaced the torque converter. You don't need a torque converter when you have an electric drive in here. So they've thrown that away and put the electric motors in the same position. So you look at the vehicle, you can hardly tell that it's a hybrid. Daimler Chrysler, who is the parent of Mercedes, is also very, very interested in the delivery truck business, and they have built some of these vehicles on their so-called Sprinter chassis. This is what it looks like. The batteries here at the back where the gas tank would normally be. Here is the variable speed drive where they run a belt that has the pulleys that open up and close and change the speed ratio. The electric motor is down here. Your gasoline engine is here. And over here is the power control unit, and there is the plug. So they have built, or in the process of building, 5 of these. One's under testing at the present time. I think it's in Germany. Number 2 and 3 will go to California. They're gasoline versions. And one will go to the Southern California Edison Company to experiment with charging up and see how that works out. And the other one will go to some of the governmental authorities for the environmental evaluations. And the 4th one will go to, is a diesel-driven unit, will go to some town in Kansas. I'm not sure where or why it went to Kansas either. But anyhow, and I don't know where the 5th one is going. They have a 2.2-liter engine. Again, relatively modest, 109 horsepower. And they have a 95 horsepower electric motor with the plug-in. And I've told you what was happening to them. At this point, I want to turn to some analysis of what's happening here and how we can handle it. If you go to the Department of Energy website, you will find a lot of information under the EIA. This is the Energy Information Administration. And among that information, they will tell you that there is about 133 million automobiles in the United States. There's about 92 million light truck-based vehicles, such as SUVs, vans, pickups, this type of thing, for a grand total of 225 million light transportation vehicles. And I'm going to group those two together for the purpose of this analysis. There is also note that 50% of all cars in the United States only go about 20 miles per day. And we can take these facts, put them together, and develop a model to try to assess in a simple-minded way what the impact of this technology could be if we charged the batteries using electricity from the utility. Now, the assumption that I have made here is that half of the cars will go 15 miles per day on the electric power. Do not use the gasoline engine. And the other half will go 35 miles per day. At that point, they will convert over to full hybrid operation with the high efficiency of the kind that we were talking about here previously. So what happens here is you do some simple arithmetic and you find out that if this happens, you have about 5.6 billion miles per day that is traveled using nothing but electricity taken from the utility. You see why the utilities might be interested in this. And that's also about 2 trillion miles a year. Numbers are staggering. My first glance at it, hey, I missed the decimal point by about 3 places, but I didn't. Okay, how much fuel is consumed? Well, I grouped the vehicles together and said they're going to get 20 miles per gallon. So if you divide this 5.6 billion miles per day by 20 miles per gallon, you're going to burn something like 281 million gallons a day, or 1.02 billion gallons per year. Now this is fuel that you could save that if you use these electric vehicles for all of the use that I described in my model here. And when you convert this into gallons, into barrels per day, you get this 6.7 million barrels per day, and it turns out that we burn about 9 million barrels a day of gasoline for these kinds of vehicles. So we're saving 74% of the gasoline that is burned in vehicles by this use of this technology for all of our travel. Well, obviously we're not going to have this anytime soon, but maybe someday we will reach half of this travel being supported with this kind of electrical system. And that could save, 37% of the oil. It's enough to put a pretty good dent in the imports of oil in the United States. Now here's some confirming figures that says that I'm not out of my mind. This is a chart I got from the Electric Power Research Institute. And over here we have plotted the number of gallons per year used by different types of vehicles, and they're all the same general shape here. We have the conventional vehicle with the blue. The yellow is the full hybrid. Then we have the plug-in hybrid that goes 20 miles per day. And then we have the plug-in hybrid that goes 60 miles per day. Let's just take the one over here, the full size. This is about 800. And here this is about, 550. And this one down here is something like 300. And the one down here is about 100. Well, we were using the 35 miles range on the vehicle that I put in my model. So it's somewhere around here. So it's about 200. And this is 800 up here. So we're 25% of that value up there. So 75% is saved, and that agrees fairly well with the 74% that I had. Let's take a big picture look at this. This is a flow of oil in the United States for the year 2003. Everything's expressed in millions of barrels per day. Here is the crude oil imports, 9.65 million barrels per day. And here is the crude oil production in the United States, 5.74 million barrels per day. And you work your way. They have various additions and subtractions along the way. But your refinery input is about 16.53. Your refining output, when you have some additions coming in here, is about 17.5. And over here, the petroleum consumption is about 20 million barrels a day, of which 13.27 is used for transportation. Keep that one in mind. Let's take a look at more detail here. The motor gasoline is 8.94, and that's the number that I used for the lightweight vehicles. Here is the distillate fuel oil, which most of it goes to make diesel fuel, but that's primarily for the heavy trucks. There aren't many light vehicles that are burning diesel fuel. These can also, but you could also convert trucks to hybrid if you wanted to. I'm not sure how practical that would be. Then down here, we have jet fuel, 1.57. So if you take the motor fuel here, some of the diesel fuel, and the jet fuel, which is primarily for commercial aircraft and military aircraft, it will come out to be about 13 million barrels per day. Now, in 2 or 3 cases recently, I've heard on the TV that 13 million barrels of fuel are being used in automobiles. Not true. It's 9 million for automobiles and light vehicles. So now, let's talk about cost. Gasoline contains about 36.5 kilowatts of thermal energy per gallon. And if you get 20 miles per gallon, you divide it into it. It takes 1.8 kilowatt hours of thermal energy from the gasoline to go 1 mile. Now, if you assume that you have a 20% efficiency overall on this system, and that's, I'm told, a very good number for that overall efficiency, you're really only using about 0.36 kilowatt hours per mile of mechanical energy at the road tire interface to drive this vehicle. Now, if you take a look at the other side of it, the electric driving it, that's a much more efficient way of doing it because you don't have the thermodynamic limitations on efficiency. It's about 70% efficient. So if you divide that number we just had by 0.7, you come out with about a little over a half a kilowatt per mile. However, we've got an unusual vehicle here that's a little heavier. It has heavy batteries in it. We have to deal with and a little larger electric motor. So I've added arbitrarily a 15% penalty, and it brings it up to about 0.6 of a kilowatt hour per mile. And if we start talking about cost, I've assumed that the cost of electricity in this kind of a configuration, semi-commercial application, is only 6 cents per kilowatt hour. That's a little less than you pay for your home. And multiply the two together and you come out at about 3.6 cents per mile. Compare that to gasoline at $2 a gallon and 20 miles per gallon. And you can see that that's about a little over 1/3 of the cost. However, that's not a fair comparison because I've ignored the tax. So let's take a look at what tax does to this. The impact of tax, if you assume that there's 35 cents per gallon of tax on gasoline that you buy today, and I don't know what it is here in Tennessee anymore, but that's a reasonable number for many states. And 102 billion gallons per year, which is the number we had earlier, it comes out there's about $36 billion a year collected for tax on gasoline. If you want to keep things even, so we're going to assess the same amount of gasoline to the electricity that's used. And when you do that, it comes out about 2.9 cents per gallon of tax. So if you add the 2.9 cents per gallon of tax to the per kilowatt hour. Add the 2.9 cents per kilowatt hour to the 6 cents that we charged, you get to almost 9 cents a kilowatt hour. And if you multiply that by the kilowatt hours per mile, you come out with a little over half a cent per mile cost. And that's still, well, 54% of what it would be gasoline at 20 miles per gallon and $2 per gallon. So you start thinking about, well, how much can I save here? And you start calculating. Well, I've got it already calculated here, plotted out. We're in the $2 per gallon range here. And you can see that if you go 35 miles, your savings is going to be somewhere around $700 per, about $600 per year. And if you're going to keep your vehicle 5 years, that's about $3,000 that you could afford to invest more than you would and still break even on it, ignoring the time value of money. On the other hand, if you get out here in the $4 to $5 range, which is what it is in Europe, and in some places it's up in the $6 per gallon range, you can see that you're up in this range, the $3,000 per year, and you could afford to put more into your hybrid configuration. Now there's two other things that we need to check here, and that is the size of the electrical capacity you must have built into your home in order to charge these vehicles at night. So we considered the worst case here, 35 miles per day, and charge it in 8 hours. And we come out with about 21.1 kilowatt hours per day. And because of the peculiar characteristics of battery charging, when the battery is the lowest level, it charges the higher current. And it could be as much as twice as fast, I'm told. So I've arbitrarily doubled that to 24 amps. And that's not an unreasonable type of value for your household. That's about what you use when you turn on all 4 burners on your gas stove. I mean, your electric stove, excuse me. So since you have typically in a modern home about 200 amp service, using 24 doesn't seem out of line. So that's not a problem. Now let's look at the other issue that's important here. How much generating capacity do we have to have in our utilities in order to charge all the batteries to go 5.6 billion miles per day? Well, if you go through the numbers here, you wind up out here with, if you're going to do this in an 8-hour day, 8 hours per day at night, or per night, you wind up with 424 million kilowatt hours, and suddenly you say, glug. And you realize that this is 424 gigawatts, and that's half of the total capacity of the United States at the present time. A real large amount of generating capacity that's going to be needed if we are going to implement this countrywide. Well, what can we do about this? First thing is this 8 hours per day. We have 3-hour time differential between the East Coast and the West Coast. So we could spread this out over 11. Well, there's nothing magic about 8 hours per day. There's nothing that says you couldn't charge 12 or 14 hours a day. And what would happen if you had to use the car before it was completely charged up? The worst that could happen is you might have to buy some gasoline for the hybrid part of your car. So realistically, even with full implementation of this throughout the country, 200 to 250,000 megawatt plants, and that would be probably over 30 years, maybe more, something of this sort. But it could very well be the coming of the second nuclear power era, because simply that there's nothing else that you could put in the United States in terms of that amount of power that would have any less impact on the environment. So that's the message I've got here, is that this is a technology that is in concert with our concept of what should happen in the nuclear power field. Now, this word is beginning to get out. This is a page out of last week's Newsweek magazine. Farid Zakara is the energy columnist for Newsweek. This is the March 7th, 2005 issue. And I've got some quotes here. There have been many calls for programs to fund research, and he's talking about the energy crisis. Beneath the din lies a little noticed reality. The solution is already with us. And that's, I guess, my message here. The solution is with us today if we want to implement it. We don't have to wait till hydrogen is handled the way it's going to have to be handled if it's going into an automobile. This could be implemented starting tomorrow, or today if you want to. The current crop of hybrid cars gets around 50 miles per gallon. Make it a plug-in and you get 75. Well, that's a little bit facetious because 75 doesn't have any meaning, as I told you before, in the context of how many miles per gallon. What you do is you optimize or minimize the use of gasoline with the plug-in hybrids for your own special situation. You can already buy a hybrid car that runs on a battery and petroleum. The next step is plug-in hybrids with powerful batteries that are recharged at night, just like laptops, cell phones, and iPods. I'm not sure what an iPod is. I hear about them all the time. Okay. I'd like to wind up with something personal and very different, but it goes back to some hybrid vehicles that we had during World War II. There were bicycles with two means of propulsion. One of the means was Briggs & Stratton 3/4 horsepower wash machine engines, and those were a lot of those laying around the country because we had just gotten electricity before the war, and people were taking these Briggs & Stratton engines out and throwing them in the junkyard and putting in 3 horsepower electric motors because they didn't have to deal with the exhaust that came out of these. And these vehicles were in use simply because there was a gasoline shortage in World War II, and this is our way of getting around it. These were built in a shop, mostly with hand tools, but I think we had an electric drill and an electric grinder, but mostly with hand tools. And they're about 4 miles each way to high school and back. And the cruising speed was about 15 miles per hour, but if you got a tailwind, you could get up to 20, but if you had a headwind, you only got about 10, and you still had to pedal like the devil to keep it going. But fuel mileage was 90 to 120 miles per gallon, but the range was only 25 miles or so because it only had a quart-sized gas tank on it. Well, this is the last slide. This is what it looks like. I can't see. The one on the left, the bicycle engine was mounted on it by my dad with a little help from me, and the one over here I put that together with a little help from my dad. So, and my brother Bill didn't contribute much to either one of them. But anyhow, so much for 1944 style hybrids. At this point, I'd be very happy to try to answer some questions.
I'll start with more of a comment. Great presentation. Really enjoyed that. And the observation that the reporter made that the tools to implement this are in hand. One of the things that in your model suggests you look into further is the life cycle of the transportation fleet, because it's quite short. I don't remember the number, but maybe in the 10 to 20 year range. And you compare that with other factors, it's not that hard for us to replace the transportation vehicles in this country, but the political impacts as well as the resource impacts on the petroleum and nuclear power, as you point out, are great. So I wonder what it will take and at what point the government will really get behind this, because there are very conflicting circles of influence there.
Well, I can give you my scenario of what's going to happen here. I think the Mercedes, or Mercedes company, with the Daimler Chrysler, has got the right approach. Companies that have delivery services of all sorts look at the bottom line. They don't get emotional about them. And if these things perform better, and they obviously will, and if they can save money on it, they're going to convert. And that's going to lead the way. Now, the present time, there's only about 200,000 hybrid vehicles in the United States. 140,000 of those are the Priuses. And Toyota has said they're going to put an additional 100,000 in the United States alone out of about 250,000 they're going to manufacture this year, 240, 250. They've obviously shown there's a market. But the extra cost, as I understand, is probably somewhere in the $300 to $500, maybe a little more than that, extra cost for the hybrid versions of the same vehicle. And part of that problem is the battery, because that's a heavy device. And if somebody can come up with a better way, better battery. People have worked on this for a long time, I know. Yeah. But anyhow, the nickel hydride seems to be the battery of choice, and with an 8-year warranty, I would assume Toyota thinks they will last that long. They're not about to replace 100% of these at 4 years. But you're right. The lifetime is turnover time on automobiles is a little over 10 years. It's been stretching out as the prices went up. It's somewhere between 11 and 12 at the present time, but it's not 25.
Even trucks are less than 20.
Yeah.
Okay.
U.S. government along with the three automakers. United States government along with the 3 automakers started the PNGV program, PNGV for the hybrid vehicles. What happened to that? Is it all wastage, or what happened really to the PNGV program? It started in 1996, the Bill Clinton's time, with the 3 large automakers. Huge amount of money was spent on the hybrid vehicles with certain ambitious goals. And now the Japanese are taking the initiative and the leadership in this area.
Well, I don't know all the ins and outs of the hydrogen program, of what's happening politically. There was a big burst of enthusiasm, a tremendous amount of money poured in, and there's been disappointing results. I might tell you that about a year ago I wrote an article that got published in the Bent of Tau Beta Pi, which is the Engineering Honor Society, and basically laid out what I saw as the problems associated with the hydrogen vehicles. And if any of you are interested in that, you can go to the Tau Beta Pi site, click on articles, and this is available through there. This presentation is written up. It will be published. The final copy has already gone to the printers, and it will be out within about 10 days for this year's spring issue of the Tau Beta Pi. If you're interested, it'll be available in about 10 days. If you can't wait, send me an email and I'll send you one.
Okay, do we have other questions or comments? Mario?
You lost me on how you handled the tax on the hybrid system. Did you take the same tax total that the government would get and spread it out?
Yeah.
I wasn't quite sure. Okay.
Yeah. Well, what I did is I determined how many miles were involved with electric vehicles under that model, my model, and then assigned an arbitrary value of 35 cents per gallon. And the end result is that it was about $36 billion that would be collected for that many gallons of gasoline, and I said we're going to apply that directly.
We have a question from the back of the room who just happens to be Dr. Uhrig's, one of his daughters.
Is the hybrid electric vehicle process a transition process before the hydrogen power, or is it a fill-in process before we actually get this started, 50 years from now? Is that how you see it?
I am not one who sees the hydrogen being implemented within a reasonable time. I see this technology being used well up into the 30, 40 years from now. That's
More acceptable?
Yeah, you don't have to change your infrastructure. You don't have to have 10,000 psi gas being fed into a hose to fill up your car. You pour in gasoline, or you connect electricity. There's a lot of details that I've had to skip over, but one of them, for instance, is if you have a device at the front of your garage where you drive up and stop, and you have a inductive coupling, you can charge your batteries without ever having to plug in anything. And these are designed and available, so you're just drive in and stop at the appropriate place, and it'll charge automatically if you want to set it up that way.
Do we have other questions or comments from the audience? Okay, from the back.
If what you're saying is right, the change between the gasoline and the electrical, it would have to be going into relying on the now electrical system. We're going in 30 years from now to do nuclear. Right now we rely around 60% carbon based electricity. 30 years from now, the hydrogen technology would actually come up to date. Fuel cells would probably by then be cheaper, more economical.
All I can say is good luck. I hope you're right. The problem at the present time, and it may be just a present problem, I don't know, but the technology that they're pushing for the automobile is relatively new technology. It has a lot of problems. The durability of it is not proven yet, and the cost is way, way too high. It's a factor of 10, if not 20 too high. And you can reduce costs by factors of 2 or 4, but 10 or 20 is very, very difficult. The cost is sort of a 1/n type thing coming down as the number of these you build increases. The cost per unit comes down predictably, but it's a long way out to where they're competitive.
Okay. Let me make a final comment. As many of you know, we've been having these colloquium presentations almost weekly for the past 5 years, and we've had some famous speakers that filled up the room. Today we set a new record. This room holds 49 people, and I count almost 70 people in here. This is a
violation.
Yeah, it's a violation. That's the reason I sit in this chair. If there's a fire, I'm the first one out the door. But I think the audience today, the local audience, is indicative of the admiration and affection that we have for the speaker today. And as most of you know, we do have a reception downstairs. Dr. Uhrig will be down there to answer more questions. You can talk one-on-one with him. But before we adjourn, let's express our appreciation again to Dr. Uhrig.